second, which contained a parameter to show that they were both solutions to the equation. You remember what we called them? Without the parameter. Very last thing I did in class last time.
Sorry, parameter
family solutions?
So when it contained the arbitrary constant, we called it a one parameter family of solutions. And then the other one without the parameter, in fact, when C was equal to 0, we called it a particular solution. Remember that? So, you remember where the parameter is coming from? Yeah. Why is the constant arising? I think I mentioned this briefly. Integration, right? So the differential equation contains a derivative. So in some way, some sense, in order to undo the derivative, we need to integrate. Whenever we integrate, we introduce an arbitrary constant. Okay. So, so our goal is always to find the family of solutions. We don't want to find a single solution because we know that there's always some family of solutions out there. Okay. Now, if say the equation contains a second derivative, what would you suspect about that family of solutions? How many derivatives do you need to undo? 2. How many times do you need to integrate? 2. How many arbitrary constants do you introduce? 2. Okay. So it turns out that whatever the order of the differential equation is, so the highest derivative that you see, the most general solution should contain that many parameters. Okay? So if you see if the highest derivative that you see is 7, then you should have 7 arbitrary constants. That would be the most general solution. Okay? So that's interesting for mathematicians. Now, I was saying that differential equations are used to model all sorts of different situations in practice. Would you want a solution like, I don't know, think of your own application that you want to solve, like I don't know, wind direction or something if you're a meteorologist. Would you want 7 parameters in your solution? No, you don't want any parameters, right? You want one specific function that models your situation. Okay? So we call these an initial value problem. If we want to determine specific values for the parameters in our specific situation, we'll need more than just the differential equation. We'll need some additional information in order to make that determination. Okay? So an initial value problem is basically just a differential equation equipped with that information. And what that information is values of the function itself and certain derivatives in order to allow us to determine those parameters. So, you can look on the page. So the first one is y double prime minus 3y prime plus 2y is equal to 0. Okay, so how many parameters would you suspect that family of solutions is going to have? 2. Okay. So you should think of those parameters in this case as unknowns, right? How much information do you need to find 2 unknowns?
2 equations. You
need 2 equations, okay? So that's why this comes with 2 initial conditions, okay? So so why do we call them initial conditions? Generally speaking, the independent variable is time. Generally speaking, we evaluate the function and its derivatives at 0. Okay, so initial meaning t is equal to 0. Now we call them initial value problems whether or not the independent variable is in fact time. Okay, and it doesn't necessarily have to be the case that we evaluate them at 0. Right? If we evaluated at 2, you could change variables in order to make the 2 change to 0. Okay, so that's the meaning of the name. So just in terms of the solution process, you should think of this as an equation equipped with enough information to determine values for all of the constants. Okay? So if you have an nth order differential equation, it will come with n parameters. You'll need n initial conditions in order to find the values of all of those parameters. Make sense? So for your purposes, what does this mean? If you later on are asked to solve an initial value problem, first you'll need to solve the differential equation. And then you substitute the initial values in order to determine the parameters. Now, we don't know how to solve any equations yet, so we'll take for granted that the function given as a solution. Or actually, let's check that this is a solution, so.
Bless you.
Okay, so this is the differential equation. These are the initial conditions. Okay, and in order for us to actually find, in order for us to find a unique solution and for that solution to exist, first of all, whatever value for the independent variable that you evaluate one of the initial conditions at, you have to evaluate all of the initial conditions at the same value. Okay? In addition to that, we always start with the function itself and build up to one less than the order of the differential equation. Otherwise, if you just picked random points, then the corresponding system might not have a solution and it might not have a unique solution. Okay, but that won't matter to you because this information will always be given to you. All right, so we're told that this is the solution and we should check, we should verify that it is. Okay, so first let's verify that this is the solution to this equation like we've been doing. So we'll need two derivatives. What's the derivative of this?
Sine.
-4 sine.
Yeah, so what do we need to use here? Chain rule, right? So, derivative, this is 4, derivative of cosine is negative sine, so minus 4 C1 sine 14. And likewise here, it's 4 C2, derivative of sine is cosine, so cosine 14. Okay, and then second derivative.
Minus 16.
Right, minus 16
C1 cosine 14.
And then here,
Minus
also
16 C2 sine 14.
Okay, so we substitute these into the equation, we don't need the first derivative. So okay, and then if you write it like I showed you over there, let's combine the terms without simplifying the coefficients. I've got minus 16 plus 16 C1 cosine plus minus 16 plus 16 C2 sine. Okay, so it is a solution. Now, how are we going to use the extra information to determine C1 and C2?
Substitute.
Yeah, if we substitute those values of t, that will leave us with an equation in C1 and C2. So, we've already done some of the work that we need. This is the function itself, right? We also need to substitute into the first derivative. We had that right here. Okay, so x of pi over 2 equals negative 2, so that's C1 cosine of 4 times pi over 2 plus C2 sine 4 times pi over 2. And we know pi over two is two pi. Cosine of two pi is one. Okay, so this is C1 times one. Okay, sine of two pi. 0. Okay, so this is a pretty simple equation. So in general, you'll have a system of equations. So each equation might contain all of the constants, but this one works out pretty easily. Okay, and then we have x prime of pi over 2. We're told that this is 1. So substitute into the first derivative. It's 4 times. Okay, this is supposed to be equal to 1. All right, so again, sine of 2 pi, this is equal to 0. This is equal to 1. So we're left with 4. C2 is equal to 1. So C2 is equal to 1. Okay, what's the meaning of all of this?
Those are particular solutions?
Yeah, this gives us a particular solution, right? This is the general solution, or the two-parameter family of solutions. The function that not only satisfies the differential equations, but also takes these values is, we know that C1 is -2, so it's -2 cosine 14. And then we know C2 is 1/4, so plus 1 with sine 14. Got it? Yes?
So what's that called right there?
This is
Is
the
that the
solution to the
solution?
initial value problem. You could call it a particular solution. So you'd say, this is the general solution to the differential equation. You would say that this is the solution to that initial value problem. All right, are you ready to try?
So catching on.
All right, try the one on the next page. This one's a little bit harder. So here I didn't really have a system to solve, right? One of the initial conditions gave me C1 exactly, the second one gave me C2 exactly. The one that you're going to work, each equation is going to contain both C1 and C2. You remember what the technique is to solve a system like that?
Elimination.
You can use elimination, or you could use a matrix, or substitution.